Hey guys, let's look at writing exponential functions from real world situations. And so to be successful in this, we want to be able to identify the starting value or the starting amount or number, which is going to be my A value, and then identify that growth or decay rate, and that can be given to us a couple different ways, and we'll look at that more in a second, but that's our B value, and then substitute those into the exponential formula. So it's important that we remember the exponential equation formula, right, is y equals a times b to the power of x. Okay, oftentimes you will see it with population. Population growth is exponential. We start with one person here, and then maybe you have 3 kids, and then those 3 kids each have multiple kids. I mean, those multiple kids then have multiple kids. So you can see the family is growing, and it just started from one person, but 3 generations later, there are a whole bunch more people. And that is exponential growth. That is a perfect example of an exponential function is population or families, looking at family trees, right? They get bigger as they go on. Or just looking at people in the world. So my A value, like I said, is going to be our starting amount. Or our initial amount, in starting value or number. Okay, and just like we've talked about, that is going to be my y-intercept. The A value is always my y-intercept in exponential functions. But it's what we're going to start with. And then my B value is that growth or decay rate. And you'll often see it written as a percentage. So I'm just going to draw a percentage sign. Or it could be words like doubled or tripled or halved. I don't know how we went to that page. Sorry, whoops, there you go. Okay, we're back. So those are just some examples, right? Again, it could be tripled as well. Okay, and then that growth is when the B value is greater than 1, and decay is when it's between 0 and 1. Okay, and how that's going to look now is this part is kind of going to be important. It's kind of going to differ once we get into real world situations. And if you're seeing a percentage, the way that we calculate growth or decay, we have to add or subtract 1 from it. Okay, so when we get into percentages, we're going to look a little bit more into how we determine that B value. But let's go ahead and get started when all values are given. Oftentimes when you see word problems, exponential functions, they're going to give you all the information you need to write the equation just in the example. So let's look at example number 1. When rabbits were first brought to Australia in the 1800s, they had no natural enemies, so their number increased exponentially. Assume there were 20 rabbits first brought to Australia, and then the population doubled each month. So there were 20 rabbits first brought, and the population doubled each month. So the number that I'm given, the first amount of rabbits that we started with was 20. That's my initial value, or my A value, right? That's that starting point. So if you want to go over here and you can also say it's the initial value. Great, and then my growth or my decay rate, it says it doubled. What does doubled mean? Well, it means it's times 2. So my growth or decay rate is 2. And if it's doubling each month, 2 is definitely bigger than 1. It is a growth. And so if I'm going to write that in my equation, I'm going to write f of x, which is going to be representing the number of rabbits, is 20, which is my initial amount, times my rate of 2 to the power of x, which is going to be the number of months. So I'm just going to say for this equation, right, f of x is number of rabbits and x is number of months, because if you remember, it says that it doubled each month. So we're looking at it in terms of months. An example number 2, it says in 1990, the population of the U.S. was about 260 million. During the early 1990s, the population of the U.S. was changing at a rate of about 1.02 annually. It tells us it was a rate of about that much. Suppose that growth remains constant. So the initial value is 260 million. And I'm going to go ahead and write it out in millions. There might be sometimes where you just write 260 and you say, okay, yeah, it was in terms of millions. And that growth or decay rate is 1.02. So this is another example of growth because it is bigger than 1. Only slightly bigger than 1, but still bigger than 1. So when I write my equation, f of x, or my y value, is the number of people. It's that population. So that's me, my starting amount, which is 260 million, times my rate to the power of x, where x is the number of years, since it says the rate annually. Number of years, and that right there is my population. Okay, but what if we're not given all of the values? Okay, and this is where the part where percentages come in, and we have to do a little bit more work in order to find that B value. Like this little heading says, it's increasing and decreasing by a percentage, and we have to find B. So let's look at example number 3. It says the starting salary for a new employee at the Thrifty Federal Credit Union is $25,000. The salary increases by 3% each year. Okay, this example that doesn't give us everything we need to know. We also need to look at the word increases. This is going to tell us whether or not we have growth or decay. So always look out for those words, either increases or decreases or grows or shrinks, right? So that we can tell whether there is growth or decay. My initial value is pretty easy to find still. It's that $25,000. That's the initial income that you're going to make. So that's $25,000. Okay, but my rate, my growth or decay rate, cannot be written as a percent. We have to change it to a decimal. So if we have 3%, that is equal to 0.03. Okay, and if you don't remember how to write a percent as a decimal, you can think either move the decimal place 2 spots to the left or divide by 100. That is literally what percent means. It means per cent. Cent is the root of for 100. So 3 divided by 100 is 0.03. Now that I have that, though, you might notice, okay, that number is between 0 and 1, but it says it increases by 3% each year, which means it's growth, right? Increases means growth. So 0.03 is not going to give me a rate that is showing growth. It's going to show decay. Okay, whenever we have an increase, we have to add 1 to my to my percentage. So in growth, and I'm going to write it up top, right, for growth, which means we're increasing, to get our B value, B equals 1 plus the rate, which that R value, plus the R value, which I'm going to use as the percent as decimal. All right, and we'll look in just a second what it would look like for decay when there is decreasing. And we'll look at that in just a second. But let's go ahead and finish. Goodness, I cannot move my screen today. Look at that. So for this problem, okay, I know that since it's increasing, I need to add 1 to it. So I'm going to take 1 and add 0.3, which just means I put it right in front. So my growth rate is 1.03. Now that's showing growth because B is greater than 1. So my equation is f of x equals 25,000 times 1.03 to the power of x, okay, where x would be the number of years, okay, and x is almost always going to be time in exponential functions. That's why if you looked at the key features at the very beginning, 5.2 lesson, it said time for x, okay. X is always, or almost always going to be time. In this case, it's years, but it's still time, and then f of x is going to be money. So if we looked at a question that said, what would an employee's salary be after 5 years? I'm going to write my equation, f of x equals 25,000 times 1.03 to the power of 5. And I can go ahead and type this entire right-hand side into my equation, into my calculator, and solve for y, or f of x, to find that salary. When I type it in my calculator, I get a salary of $28,981 and about 85 cents. Let's look at example number 2. Example number 4. In 1980, there were 1,200,000 elephants living in Africa. The number of elephants has decreased by about 6.8% per year. So now we are looking at a decreasing by that 6.8 per year, okay, an initial amount of 1,200,000 elephants. So if we have that as an initial value, now we're looking at growth and decay rate, okay? If it is decreasing, in order to find that B value, we must take 1 and subtract that rate written as a percentage. It's a decimal, okay? So R, again, just represents the percentage as a decimal. So if I take my decimal here, 6.8%, that is going to translate to 0.068. Okay? In decreasing situations, I do 1 minus 0.068 in order to find my B value. That is going to give me a B value. B value that is 0.932, which is less than 1. So we know that it is going to be decay, which is why it's decreasing. And then I can go ahead and write my equation from there. X again is representative time for year, and then I can use this equation to find out how many elephants there will be in 1976. I have to look at this one to see, okay, what is, how many years have passed from 1980 to 1976. That seems to be working backwards, actually. Which is kind of weird. I think that is actually supposed to be 86. So I'm going to change it for 86 for this problem. So in 86, that is 6 years later. So I'm going to plug in 6 for X, and let's see how many elephants are going to be living in 1986. So 6 years later, there's going to be roughly 786,460 elephants left in Africa. Okay, go ahead and make sure you make note at the top up there so that you understand how to find the B value if it is not directly given to in the equation. Okay, if it gives it to you as a percent, you're going to have to either add 1 or subtract from 1 to find that B value. Let your teacher know if you have any questions.